Download this code from codegive.com, link in the description below. Design and implementation of a mini DC motor speed control system. This tutorial will guide you through the design and implementation of a mini DC motor speed control system using a microcontroller, Arduino Uno for example, a motor driver, a DC motor, and a feedback mechanism, like an encoder. We'll cover the theory, component selection, circuit design, code development, and finally, testing and tuning. Introduction and system overview. A DC motor speed control system aims to regulate the rotational speed of a DC motor to a desired set point. This is crucial in applications requiring precise control over movement, such as robotics, automation, and CNC machines. Our system will work as follows. 1. User input *. The user sets a desired speed, example using a potentiometer or serial input. 2. Setpoint *. This desired speed is converted to a target speed value, example RPM or encoder ticks per second. 3. Feedback *. An encoder attached to the motor shaft provides real-time information about the motor's actual speed. 4. Error calculation *. The system calculates the difference between the setpoint, desired speed, and the feedback, actual speed. This is the error signal. 5. Control algorithm, PID. A proportional integral derivative, PID, control algorithm uses the error signal to determine the appropriate control signal to send to the motor. 6. Motor driver *. The control signal, typically a PWM, pulse width modulation, signal, is fed to a motor driver, which amplifies the signal and drives the DC motor. 7. Motor response *. The motor's speed changes in response to the control signal. 8. Loop iteration *. The process repeats continuously, constantly adjusting the motor's speed to match the set point. 2. Component selection. 1. Microcontroller *. Recommendation * Arduino Uno, Arduino Nano, or similar. Reasoning * Arduino is widely used, has a large community support base, and offers ease of programming. Its built-in PWM outputs are perfect for motor control. Requirements * Adequate number of GPIO pins, at least one PWM output, and sufficient processing power. 2. DC motor * Selection criteria * Consider the voltage rating, speed range, RPM, torque, and physical size required for your application. Many motor examples * Small geared DC motors are often used in robotics. A common choice is a 6V or 12V DC gear motor. Specifications * Read the motor's data sheet for its operating voltage, stall current, and no load speed. This information is critical for selecting a motor driver. 3. Motor driver *. Recommendation * L298N, TB6612FNG, or DRV8833. Reasoning * These are popular and readily available motor driver ICs. Key considerations Voltage rating * must match or exceed the motor's voltage. Current rating * must be able to handle the motor's stall current, the current drawn when the motor is stalled. Always choose a driver with a current rating significantly higher than the motor's stall current to avoid damage. Logic level * The driver's logic level, typically 5V or 3.3V, must be compatible with the microcontroller's output. Control signals * Understand the control signals, example enable, in 1, in 2, required to control the motor's direction and speed. 4. Encoder, optional, but highly recommended for closed-loop control. Type * Quadrature encoder. Asterisk function asterisk provides feedback on the motor's rotational position and speed. Asterisk resolution asterisk measured in pulses per revolution, PPR. Higher PPR provides more accurate speed control. A PPR of 100 or more is generally good. Asterisk interfacing asterisk typically has two output channels, A and B, that produce quadrature signals. The relative timing of these signals indicates the direction of rotation. Asterisk important note asterisk consider if your motor already has an integrated encoder. If so, use it. 5 Power supply asterisk. Asterisk voltage asterisk must match the motor's voltage rating. Asterisk current capacity asterisk must be able to supply the motor's stall current plus the microcontroller's current draw, and motor driver needs. Asterisk regulation asterisk a regulated power supply provides a stable voltage, which is essential for consistent motor performance. 6 Potentiometer, 4-speed setpoint, optional. Asterisk value asterisk typically 10 ohm. Asterisk connection asterisk connect the outer pins to VCC and GND, and the center pin to an analog input pin on the Arduino. 7 Other components asterisk. Asterisk resistors, for pull-up/pull down if needed. Asterisk connecting wires. Asterisk breadboard or PCB, for prototyping/permanent circuit. Asterisk multimeter, for testing. 3. Circuit design. Here's a circuit diagram example using an Arduino Uno, L298N motor driver, DC motor, and a quadrature encoder. Explanation asterisk. Asterisk potentiometer asterisk connected to an analog input, A0, to read the desired speed setpoint. The voltage read from the potentiometer is mapped to a speed range. Asterisk encoder asterisk channels A and B are connected to digital pins 2 and 3 on the Arduino. These pins are configured as interrupts to capture encoder pulses. Using interrupts ensures accurate speed measurement, especially at high speeds. Asterisk L298N asterisk the L298N motor driver is used to control the DC motor. Asterisk enable A, ENA, pin is connected to a PWM pin on the Arduino, pin 9. This pin controls the motor's speed through PWM. Asterisk in 1 and in 2 pins are connected to digital pins 8 and 7 on the Arduino. These pins control the motor's direction. Asterisk DC motor asterisk connected to the output A and output B terminals of the L298N. Asterisk power asterisk the Arduino and L298N have separate power supply connections. Make sure the voltages are correct. The L298N needs power to drive the motor, VS, and to operate its logic, VCC. 4. Code implementation, Arduino. This Arduino code example implements a PID control loop to regulate the DC motor's speed. Code explanation asterisk. 1-pin definitions asterisk defines the Arduino pins connected to the motor driver, encoder, and potentiometer. 2 variables asterisk declares variables for encoder counts, speed, PID gains, PID terms, and target speed. 3 setup, function asterisk. Asterisk initializes serial communication for debugging. Asterisk sets the pin modes for motor control and encoder pins. Asterisk attaches interrupt routines to the encoder pins. The attach interrupt function tells the Arduino to execute the encoder event function whenever the signal on encoder pin A or encoder pin B changes, rising or falling edge. Asterisk sets the initial motor direction. For loop function asterisk. Asterisk the loop function is the main program loop. Asterisk timer-based execution asterisk the if, now, last time equals sample time, block ensures that the speed calculation and PID control loop are executed at a fixed time interval, specified by sample time. This is crucial for stable PID control. Asterisk calculate speed, calculates the motor's speed in RPM based on the encoder pulses. Asterisk adjust motor speed, implements the PID control algorithm and adjusts the motor's speed using PWM. Asterisk read potentiometer, reads the potentiometer value and maps it to a target speed. Asterisk print debug info, prints the target speed, current speed, and PWM output to the serial monitor for debugging and tuning. 5. Encoder event, function asterisk. Asterisk this is an interrupt service routine, ISR, that is executed whenever the encoder signals change. It must be short and efficient. Asterisk reads the states of encoder channels A and B. Asterisk determines the direction of rotation based on the quadrature relationship between A and B. Asterisk increments or decrements the encoder count variable accordingly. This variable keeps track of the total number of encoder pulses. 6. Calculate speed, function asterisk. Asterisk calculates the motor's speed in RPM based on the number of encoder pulses counted within the sample time. Asterisk calculates revolutions based on the encoder count and the encoder's pulses per revolution, PPR. Asterisk calculates the speed in RPM. The formula revolution / time change / 60,000.0 converts the revolutions per millisecond to revolutions per minute, RPM. Asterisk resets the encoder count and last encoder time variables for the next speed calculation. 7. Read potentiometer, function asterisk. Asterisk reads the analog value from the potentiometer, range 0 to 1023. Asterisk uses the map function to map the potentiometer value to a desired speed range, 0 to 100 RPM in this example. Adjust this range to suit your application. 8. Adjust motor speed, function asterisk. Asterisk implements the PID control algorithm. Asterisk error calculation asterisk calculates the difference between the target speed and the current speed. Asterisk integral term asterisk accumulates the error over time. This helps to eliminate steady-state errors. The integral term is limited to prevent integral wind-up, where the integral term becomes excessively large, causing oscillations. Asterisk derivative term asterisk calculates the rate of change of the error. This helps to dampen oscillations and improve the system's response time. Asterisk PID output asterisk calculates the PID output based on the proportional, integral, and derivative terms, multiplied by their respective gains, Kp, K, Kd. Asterisk output limiting asterisk the constrain function limits the PID output to the PWM range, 0 to 255. This prevents the output from exceeding the motor driver's capabilities. Asterisk motor control asterisk sets the motor direction based on the sign of the PID output. Asterisk analog write, enable pin, int, ABS, output, sends a PWM signal to the enable pin to control the motor's speed. The ABS function is used to ensure that the PWM value is positive, even when the output is negative, for reverse direction. Asterisk updates the last error variable for the next PID calculation. 9. Set motor direction, function asterisk. Asterisk sets the motor's direction based on the input dir, true for forward, false for reverse. Asterisk controls the in1 pin and in2 pin of the L298 and to set the desired direction. 10. Stop motor, function asterisk. Asterisk stops the motor by setting the enable pin low, disabling the PWM signal. 11. Print debug info, function asterisk. Asterisk prints the target speed, current speed, and PWM output to the serial monitor. This is invaluable for debugging and tuning the PID controller. Important notes asterisk. Asterisk encoder PPR asterisk the PPR variable in the calculate speed function must be set to the correct pulses per revolution of your encoder. This is crucial for accurate speed measurement. Asterisk gear ratio asterisk if your motor has a gearbox, you may need to account for the gear ratio in the calculate speed function. The formula would become revolutions equals float encoder count slash float PPR asterisk gear ratio. Asterisk interrupts asterisk using interrupts for the encoder is critical for accurate speed measurement, especially at higher speeds. Make sure your ISR, the encoder event function, is short and efficient. Asterisk PWM frequency asterisk the PWM frequency used by analog write on the Arduino Uno is approximately 490 Hz. This is generally suitable for DC motor control, but you can change it if necessary, using timer registers. A higher PWM frequency can reduce motor noise but may require more processing power. Asterisk compile and upload asterisk verify and upload the code to your Arduino board. Testing and tuning. 1. Initial testing asterisk. Asterisk connect all the components according to the circuit diagram. Asterisk upload the code to your Arduino. Asterisk open the serial monitor in the Arduino IDE, tool serial monitor. Asterisk observe the output. You should see the target speed, current speed, and PWM output being printed to the serial monitor. Asterisk rotate the potentiometer and observe if the motor's speed changes accordingly. Initially, the motor may not respond well because the PID gains are not yet tuned. 2. PID tuning asterisk. PID tuning is the process of finding the optimal values for the proportional, Kp, integral, K, and derivative, Kd, gains to achieve the desired motor control performance. There are several methods for PID tuning, but here's a common iterative approach. Asterisk start with proportional, Kp. Asterisk set K and Kd to 0. Asterisk increase Kp gradually until the motor starts to oscillate, overshoot and undershoot, around the target speed. The serial monitor output is crucial here. Asterisk reduce Kp until the oscillations are minimized. This is your starting Kp value. Asterisk add integral, K. Asterisk increase K slowly until the motor reaches the target speed without any steady state error, the motor speed eventually matches the target speed. Asterisk if K is too high, the motor will oscillate again. Reduce K until the oscillations are minimized. Asterisk add derivative, Kd. Asterisk increase Kd slowly to dampen the oscillations and improve the system's response time. Asterisk Kd helps to prevent overshoot. If Kd is too high, the motor will become sluggish and unresponsive. Asterisk iterate asterisk repeat the process of adjusting Kp, K, and Kd until you achieve the desired performance. You're looking for a balance between fast response, minimal overshoot, and stability. Tips for PID tuning asterisk. Asterisk observe the motor's behavior asterisk pay close attention to how the motor responds to changes in the set point. Is it too slow, too fast, oscillating, or unstable? Asterisk use a systematic approach asterisk don't just randomly change the gains. Follow a systematic approach, like the one described above. Asterisk adjust gains in small increments asterisk make small adjustments to the gains and observe the effect on the motor's performance. Asterisk consider your application asterisk the optimal PID gains will depend on the specific characteristics of your motor, load, and application. You may need to experiment to find the best values. Asterisk use tools, optional there are software tools available that can help with PID tuning. These tools can analyze the system's response and suggest optimal gain values. 3. Troubleshooting **** motor not spinning ****. Check the power supply connections and voltage. Verify that the motor driver is properly connected and powered. Check the Arduino's output signals to the motor driver. Make sure the enable pin is set high and that the in1 pin and in2 pin are configured correctly for the desired direction. Test the motor directly with the power supply to ensure it's working. Motor spinning erratically ****. Check the encoder connections and signals. Make sure the encoder is properly aligned and not slipping. Verify that the interrupt routines are working correctly. Check the PID gains. They may be too high, causing oscillations. Inconsistent speed control ****. Ensure that the power supply is stable and providing a consistent voltage. Check for noise in the encoder signals. You may need to add filtering capacitors. The sample time might be too long. Try reducing sample time. 6. Advanced considerations ****. Current limiting **** Implement current limiting to protect the motor and motor driver from overcurrent conditions. Many motor drivers have built-in current limiting features. Load compensation Implement load compensation to maintain consistent speed under varying loads. Advanced control algorithms Explore more advanced control algorithms, such as feed-forward control, adaptive control, or model predictive control, for improved performance. Sensor fusion Combine encoder data with other sensors, such as accelerometers or gyroscopes, to improve the accuracy and robustness of the speed control system. Communication protocols Implement communication protocols, such as UART, SPI, or I2C, to allow the microcontroller to communicate with other devices or systems. This comprehensive guide provides a solid foundation for designing and implementing a mini DC motor speed control system. Remember to adjust the code and parameters to suit your specific application and hardware components. Good luck.